There's more of it in the universe than there is of everything you can actually see, 6 times more, and yet not a single telescope, not a single laboratory, not a single instrument built by human hands has ever directly detected it. For over 90 years, dark matter has been the biggest open case file in cosmology, a substance we're confident exists because of what it does to everything around it, while remaining completely invisible to every method we've ever used to look for it directly. Then, in November 2025, a researcher scanning through more than a decade of satellite data found something that had never shown up before. A strange, structured pattern of gamma rays, shaped almost exactly like the invisible halo dark matter is supposed to form around our own galaxy. The question every physicist is now asking is simple and enormous at the same time. Did we finally just catch a glimpse of the thing that built the universe? To understand why the signal matters so much, you have to go back to where the mystery actually began, in 1933. With a Swiss astronomer working at Caltech named Fritz Zwicky. Zwicky was studying the Coma Cluster, a dense grouping of galaxies near the Milky Way's North Pole, using the same telescope at Mount Wilson that Edwin Hubble had recently used to prove the universe itself was expanding. By measuring how the light from individual galaxies in the cluster had been stretched, redshifted on its way to Earth, Zwicky could calculate how fast each galaxy was moving. What he found didn't make sense. The galaxies inside the cluster were racing around at speeds exceeding 2,000 kilometers per second, fast enough that the entire cluster should have flown apart long ago. The individual galaxies flung off into the void like rocks let loose from a spinning sling. When Zwicky calculated the total gravitational pull of all the visible stars and gas in the cluster, the numbers simply didn't add up. The visible matter provided nowhere near enough gravity to hold everything together at those speeds. By his estimate, the cluster needed roughly 10 times more mass than anyone could actually see in order to stay bound together at all. Zwicky concluded that something else had to be there, something with real gravitational weight, but completely invisible to any telescope of his era, or, as it would turn out, to any telescope built in the 90-plus years since. He called it dunkle materia, dark matter. The core problem with dark matter, the reason it has resisted direct detection for nearly a century, comes down to its defining property. It doesn't interact with light in any way. It doesn't emit light, doesn't reflect light, doesn't even absorb light, in a way that would cast a shadow we could photograph. Since virtually every method astronomers use to study the universe depends on light in one form or another, dark matter is, by its very nature, built to be invisible to the primary sense we use to explore the cosmos. What we can observe over and over in galaxy after galaxy and cluster after cluster is its gravitational fingerprint. The way it bends the paths of visible stars and gas, the way it holds galaxies together that would otherwise fly apart, the way it distorts and magnifies light from far more distant objects passing near it. We know something is there because of what it does. We still don't know what it actually is. Of the leading candidates physicists have proposed over the decades, one class of particle has generated the most sustained interest. WIMPs, short for weakly interacting massive particles. These are hypothetical particles predicted by an extension of the standard model of particle physics called supersymmetry. And on paper, they check nearly every box scientists are looking for. They would barely interact with ordinary matter except through gravity. They wouldn't emit or absorb light. And they would carry genuine mass, exactly the kind of quiet, gravity-only presence that could explain what Zwicky first noticed in the Coma Cluster nearly a century ago. The theoretical path to actually detecting a WIMP runs through a process called annihilation. Every particle in the standard model has a mirror image antiparticle, identical in mass but opposite in charge. And when a particle meets its antiparticle, both are destroyed in a burst of energy, typically released as gamma rays. If WIMPs exist and occasionally collide with other WIMPs throughout the galaxy, that annihilation should, in theory, produce a very specific and predictable pattern of gamma ray energy, one tied directly to the WIMP's actual mass, something physicists currently estimate could fall anywhere between roughly 10 and several thousand times the mass of a single proton. Gamma rays are genuinely useful clues for astronomers, but they come with a serious complication. They aren't unique to dark matter annihilation. The universe produces gamma rays constantly through the superheated material spiraling into black holes, through the violent final moments of dying stars, through countless ordinary astrophysical processes that have nothing to do with dark matter at all. Finding a genuine WIMP signature buried inside that noise means painstakingly identifying and subtracting every known source of gamma rays from an enormous dataset, then seeing whether anything unexplained is still left over. That's precisely the project Dr. Tomonori Totani, an astrophysicist at the University of Tokyo, took on starting in early 2024, working through more than 15 years of accumulated data from NASA's Fermi Gamma Ray Space Telescope, an instrument built specifically to catch gamma ray bursts from across the universe. Our own galaxy is a flat, spiral disk, meaning most of its visible matter Its stars, its gas, its densely packed galactic center sits concentrated along a relatively thin plane. Naturally, most conventional sources of gamma rays cluster there too, but the way stars and gas actually move throughout the galaxy suggests dark matter isn't confined to that flat plane at all. Instead, it appears to surround the entire Milky Way in a vast, roughly spherical structure astronomers call the halo. By carefully excluding the gamma-ray-saturated galactic center and systematically removing every known astrophysical source, one by one, from the remaining 15 years of Fermi data, Totani was left with something researchers describe as genuinely startling. A distinct pattern of leftover gamma rays arranged in almost exactly the shape predicted for the Milky Way's dark matter halo, and the energy of that signal wasn't random. It peaked at around 20 giga-electron-volts, sitting squarely inside the range physicists would expect from WIMP annihilation. If this signal really does come from WIMPs colliding and annihilating throughout our galaxy's halo, the implications are difficult to overstate. It would represent the first observational evidence ever for one of the two leading candidates for what dark matter actually is, closing a chapter of cosmology that has remained open since Zwicky's original 1933 measurements. But before anyone can responsibly declare the case solved, several serious complications remain. The first is uncertainty in the WIMP's own predicted mass. Because WIMPs remain entirely theoretical, with no confirmed direct detection anywhere, from underground detectors to particle colliders, physicists are still working within a fairly wide range of possible masses, which means the correct energy signature to expect from annihilation isn't pinned down with total precision either. The second, arguably more serious concern involves sheer numbers. Producing a gamma-ray signal as strong as the one Totani measured would require a significantly higher local density of WIMPs than most existing models, built using evidence from the early universe, like the cosmic microwave background, currently predict should be there at all. This is exactly the kind of tension that makes serious physicists cautious, even when a result looks genuinely exciting. Professor Carlos Frank, one of the original theorists behind the WIMP dark matter model, and a researcher who has spent decades pursuing exactly this kind of evidence, has compared the eventual confirmation of dark matter's true identity to the significance of Darwin's theory of evolution for biology, a discovery so foundational that nobody should claim to have made it until the evidence is airtight. For now, researchers describe the WIMP explanation as a strong contender, by some assessments the strongest currently on the table, but not yet a closed case. So what happens next? If WIMP annihilation really is responsible for Totani's signal, the same telltale gamma-ray pattern should, in principle, show up in other dark matter-dominated systems too, particularly the small ancient dwarf galaxies that orbit the Milky Way, and potentially in galaxy clusters farther beyond. Confirming or ruling out the signal will require exactly that kind of independent cross-check, applied across multiple different targets rather than relying on a single dataset alone. Help may already be on the way from an entirely different direction. The Vera C. Rubin Observatory, named for the astronomer whose meticulous studies of galaxy rotation in the 1970s first brought serious, sustained scientific attention to dark matter as a real phenomenon worth investigating, came online in Chile in June 2025. Over its planned decade-long survey, the observatory will photograph the entire visible southern sky repeatedly, generating roughly 20 terabytes of new image data every single night, an amount of information that will eventually accumulate into more than 60 petabytes, the equivalent of 60 million gigabytes, by the survey's end. That flood of new observational data, covering galaxies, clusters, and gravitational lensing effects across a huge swath of the sky, will give researchers an entirely new set of independent measurements to test whether the pattern Totani found in Fermi's gamma-ray data is genuinely dark matter, or something else still hiding in the noise. There's a reason this particular mystery has occupied physicists for nearly a century without resolution. Dark matter isn't some minor footnote in our understanding of the universe. It makes up more than 80% of all the matter that exists, and its gravity was essential in pulling the first stars and galaxies together out of the smooth, nearly featureless gas that filled the infant universe. Without it, structures like our own galaxy likely wouldn't have had enough gravitational scaffolding to form at all, at least not on anything like the timescale we observe. Whatever dark matter actually turns out to be, it has been quietly shaping the architecture of the entire cosmos since almost the very beginning, and it will keep shaping what happens to that cosmos far into the future. For now, the case remains open, but for the first time in a very long while, there's a specific, concrete lead, a real signal found in real data, sitting exactly where theory predicted dark matter's halo should be, with an energy profile that matches one of our leading candidates for what it might actually be made of. Whether this turns out to be the long-awaited breakthrough, or simply another tantalizing false alarm in a search that has produced plenty of them before, researchers across multiple continents, from underground laboratories to satellites in orbit to a brand new observatory high in the Chilean mountains, are now racing to find out. 90 years after Fritz Zwicky first noticed galaxies moving in ways gravity alone couldn't explain, we may finally be closing in on an answer to the question he first asked: what exactly is holding the universe together